Organised today. I was a bit late from a meeting. So, where are we in the lecture notes? So, where we finished on Friday of last week was on chapter 3. We're up to slide 84 of chapter 3 on independent random variables. So, what have we been doing? So, we've been looking at the notion of a probability mass function and a probability density function for random variables x. So remember what a random variable is. It's a function from the sample space S into the real line. The set of values of which that random variable can take can be countable or countably infinite, i.e. discrete, or it can lie in a continuum of values, i.e. it's continuous. And in order to describe probabilities associated to such random variables, you can use the notion of a probability mass function representing the probability that the discrete random variable has a particular value, or the associated density function, which can be used to compute probabilities through integrals. And what we looked at last time was the notion of where we had a pair of random variables x and y, where x and y are either both continuous or both discrete, and how we could basically do some calculations with that. So for example, here where we're computing probabilities and so on and so forth. So that's where we finished last week. So now what we're doing is we're looking at the notion of independent random variables. So remember the notion of independent events was essentially the notion that you take events A and B, and if A does not affect B in a kind of some sense, then A and B are said to be independent events. Or if you prefer, the probability of A intersection B is equal to the probability of A times the probability of B. Okay, and so what we're going to do now is to formalize this notion to random variables. Okay, so we start with a definition. So remember that we have a pair of random variables, x and y. X and y are potentially real valued or in some subspace of the real line. And they're said to be independent. If you look at the joint probability mass function or density function, so remember this is the joint PMF or PDF of x and y, and we can say that the joint PDF or PMF of x and y is equal to the product of the pair of the marginals for every point x and y which lies in the sample space. So that says it's very similar to the notion I just mentioned with respect to events. So remember, events are independent if their probability of their intersection is equal to the probability product of their probabilities. It's the same thing, almost the same thing for random variables. You can just express, if you can express the joint as the product of the marginals for every sample point. So this has to be true for every x and y in your sample space. If there exists a single x and y for which this equation as highlighted in red is not true, then they are not independent random variables. Okay, and that's for two random variables. And the clear extension for the case we have little n random variables, so now you have a sequence of random variables x1, x2, all the way up to x little n. They are said to be independent if and only if. Okay, so remember this is if and only if, so I'll explain that in a moment. If I take the joint PDF or joint PMF of these random variables, they're equal to the product of the marginals. Okay, so remember what the if and only if means. It says if I have this equation, x and y are independent, or if x and y are independent, they imply this. So essentially what you can do in order to check independence is simply enough to verify this equation for every x and y. And if you find a pair x and y, or here x1 up to xn, for which this does not hold, or this one does not hold, then they are not independent. Okay, so it's a simple thing to do. Once you have this construction, you can verify independence or not. Okay, I think I don't really understand this slide. Well, it's a kind of trivial remark. The product of two positive functions, f of x and f of y, means a function which is positive on a product space. I mean, this is clear because we were working on product spaces from the beginning. I don't really find this remark very useful. Okay, let's look at some examples because we're going to learn something more interesting along the way. So look at a joint probability mass function, not PDF, probability mass function is given as follows. Okay, so x is a random variable which can take the value 2 or 4, and y is a random variable which can take the value 1, 3, or 5. Remember what, for example, this entry represents is the probability that y is equal to 3 and x is equal to 2, so it's a 0.2. So remember that we can compute the marginals of x and y. So the marginal of the x, probability that x is 2 is 0.1 plus 0.2 plus 0.1 is 0.4. The probability x is 4 is 0.15 plus 0.3 plus 0.15 is 0.6. And similarly for y, we just sum across the rows. So the probability y is 1 is 0.25. The probability y is 3 is 0.5, and so on and so forth. Okay, so in this table we have represented both the joint probability mass function, i.e. these white numbers in white, and the marginals are at the end of the column. This is for x, and at the bottom of the bottom row is the probability mass function for y. Okay, and what we're asked the question is, are the random variables x and y independent? Okay, so this is a kind of tedious case, but we can check this. Okay, so we start first of all, f of x is 2 and f of y is 1. Okay, so what that means is f of x is 2 is 0.4, f of y is 1 is 0.25. Okay, now we multiply those two numbers together, that's 0.1. Now let's look at the corresponding entry of the joint probability mass function of x and y. So this is the probability x is 2 and y is 1 is 0.1. Okay, so in this case I get 0.1. So the probability of the marginals to f of x is 2, probability y is 1 is equal to the joint probability. Okay, but at this stage we have not established that the random variables of x and y are independent. We've only verified the equation, i.e. this one, in the case that x is equal to 1 and y is 2, I think, or the other way around. X is 2 and y is 1. Okay, now what we have to do is to verify this equation for all the other cases. Okay, so that is to say, that there are 6 cases, 6 positions in this joint probability mass function, and we now need to check, for example, if y is 1 and x is 4, the probability that y is equal to 1 is 0.25, that x is equal to 4 is 0.6. So if we multiply this one by this one, we have to get this one, otherwise they're not independent. Okay, so for example here it says x is 2, y is 3, is a strange place to start. Y is 3, x is 2 is 0.2, 0.4 times 0.5 is 0.2, and you can check, for example, 0.1 is equal to 0.4 times 0.25. Here, 0.6 times 0.25 is 0.15. So if you go through all the other 5 other entries of that table, you can verify that the joint probability mass function of x and y is equal to the product of its marginals. Okay, so just in case you're wondering again, this, for example, this notation means f sub x4 is the probability that the random variable x takes the value of 4, and you can check is 0.6. Okay, so for every single sample point here, and there are 2 times 3, 6 possible sample points of the random variable, one has indeed that the joint probability mass function is equal to the marginals. So that is to say, for any entry here, it's equal to this one times this one, this entry is equal to this one times this one entry is equal to this one times this one. And that's true for every pair, those 6 pairs. So that is to say that these random variables are independent. So we had to verify for every pair x and y which lie in the support or range of these random variables that precisely we have the equality which we need. Okay, example 2. So example 2, so that's example 1 in section 3.2.1, which was the joint probability mass function of a pair of random variables x and y, which had the probability mass function xy over 36, where x can be 1, 2, 3, and y can be in the set 1, 2, 3. So there are 9 possible sample points. The question is, are x and y independent? Well, you might remember, I think we have already computed the marginals, and that's what we'll do that again, and we'll show or discuss whether or not the marginals, the product of the marginals is equal to this thing. In fact, one can kind of guess from the beginning that they probably are, because this function is the form of something times x times something times y, and normally these things tend to be independent, but we have to check it to be certain. Okay, so let's start with the marginal probability mass function of x. Okay, so the marginal probability mass function of x, remember you take the joint PDF of x and y, and what you do is you sum over the support for the random variable y. So here, remember, y can take the value 1, 2, or 3. So this is the joint PMF, 1 over 36 times x times y, and we're summing over y from 1 to 3. Okay, so this summation is not too difficult. We can take out the factor x over 36. These are both constants, so they come outside the sum. And we have the sum y is equal 1 to 3 of y, which is 1 plus 2 plus 3, which is 6. So we get x over 36 times 6. 6 over 36 is 1 over 6. So the marginal PMF for x is x over 6, where x can be 1, 2, or 3. Okay, we fixed x, and x has to lie in that set, otherwise we get 0. Okay. Now, the calculation for y is identical, but let's do it just for kicks, I suppose. So f sub y super of y, so we fix y to be in the set 1, 2, 3. Now we want to find the marginal probability mass function for y. So what that means is, again, we write down the joint probability mass function for x and y. We know that was specified at the beginning. And we sum over all possible values of x. So x could be 1, 2, or 3. This is the same calculation we had before, but let's do it one more time. So in this context, y over 36 is a constant, so we can take that outside the summation. And now we're computing the sum x is equal 1 to 3 of x, and that's equal to 1 plus 2 plus 3, which is 6. So y over 36 is y over 6, is the marginal probability mass function for y when y lies in the set 1, 2, and 3, or it's 0 otherwise. Okay, so those are the marginal PMFs for x and y. Now, what was the point? Remember, what we were trying to do is to work out whether or not the random variables x and y are independent. So what that means is if I multiply this one by this one when x lies in the set 1, 2, and 3 and y lies in the set 1, 2, and 3, that should be equal to the joint probability mass function. Otherwise, they are not independent. Okay, so f of xy is equal to this one. F of x times f of y is this thing. And so these things are equal for every x and y in the set 1, 2, 3, respectively. So what that means is x and y are independent random variables. Okay, remember that if this equation does not hold for one x and y, it is the case that x and y are not independent. So we have to verify it for all x and y. Okay, so example 3 is slightly different, not difficult. X and y are two independent random variables, and they have a PDFs, they're continuous. Fx of x is e to the minus x, Fy of y is e to the minus y. X and y are respectively positive, otherwise the density function is 0. Okay, and this is a known probability density function. It's called the exponential density. I think we discussed that in chapter 4. And we are asked to find the joint PDF of x and y. Okay, this is straightforward. The answer is I multiply this one by this one, and x and y are both non-negative, and otherwise we get 0. Okay, because x and y, so then that was a word explanation. Let's just spend a little bit of time to verify this. So we know x and y are independent. That means that for every x and y, the joint PDF of x and y is equal to the product of the two marginals, and that's equal to e to the minus x times e to the minus y if x and y are both positive, and otherwise we get 0. Okay, so if you want, you can just tidy up the exponential, and that gives you the joint PDF. Okay, hopefully this is kind of, these examples hopefully give you an indication of when to verify random variables x and y are independent, because basically you can factorize the joint into products of functions of x and y. Okay, when you can do that, that gives you a good clue that the pair of random variables are independent. Okay, let's have a look at another example. So here we have a joint PDF x and y, for which is equal to 2 times x plus y, if x and y are in this region. So x is between 0 and 1, and y is strictly less than x but bigger than 0. Okay, so this is the shady region. This is where the density function lives on in 2D, and then there's a third dimension which draws this curve. Okay, so x lies between 0 and 1. Y is strictly less than x, so if we draw the line y equals x, okay, y lies below this line. So this is the shaded region in which the density function is non-zero. Okay, otherwise the density function is 0. Okay, so we would have a third dimension. You could imagine, sorry, I'm pointing to it. You'd have a third dimension coming out of the page, which would be the line z is equal x plus y, which will only be non-zero over this shaded region. Okay, so you would have some sort of 3D curve. Okay, and now we're asked the question, are x and y independent? Okay, now this type of example, so for me, obviously I've been doing this for a long time, but I can tell you instantly they're not. And one way to work that out, of course we're going to do the question, but let me just tell you why I think that's the case. Because the range of y is intrinsically linked to x. Okay, so once there's a dependence between x and y, I'm pretty sure they can't be independent. But let's see if that's the case. Okay, first of all, let's find the marginal PDF of x. Okay, so the marginal PDF of x basically is equal to, so we don't care about this. This is an unnecessary line. We never need this. We already can just say from the beginning that x is between 0 and 1 because it is. Okay. Otherwise, we don't care. Okay, so the marginal PDF of x is the joint PDF of x and y integrated over the entire region of y. Okay, so basically we only care about, we only care about the integral under this curve. Okay, so now I'm integrating under this curve 2 plus xy with respect to y, and y goes between, is in this shaded region. So in order to compute the integration range for y, what one does is draws a vertical line parallel to the y-axis with an arrow pointing upwards. So, and we work out where it enters this shaded region. So it enters this region at y equals 0, and it leaves this shaded region when y is equal to x. So the integration limits are the integration between 0 and x. Okay, and that's the only tricky part. So now we are fixing x in 0, 1, and we have to compute this integral with respect to y between the limit 0 to x for x fixed. Okay, so now this is straightforward. This is 2x times y, that's what you're going to get there, and this is 2y, so that's y squared over 2 times 2, so you don't have to take that, but you can look at it like there. Okay, so if you differentiate this function, you'll get back to that. Hopefully it's relatively clear. Okay, and then we just evaluate the integral. Again, as usual in our cases, if you set y equal to 0, we kind of knock the whole thing out. So we just evaluate this functional when y is equal to x. And if you evaluate when y equals x, I get x times x, that's x squared, plus x squared over 2 multiplied by 2 is 3 over 2 x squared when x is in the interval 0 to 1. Okay, so that's a good exercise in computing a marginal. So that's the marginal in x. Now we have to compute the marginal in y. Okay, so the marginal in y, again, the marginal in y is the joint density function, which is this thing, integrated over the region of the x region, right? And so y we again fix. So what is the x region we integrate? So now what I want to do is I take this function, now I want to integrate it with respect to x. Okay, so now if I integrate with respect to x, I draw a line parallel to the x-axis with the arrow pointing right as I look at it, or probably right as you look at it as well. Okay, and we work out where it enters and leaves the region. So this straight line parallel to the x-axis enters this in the point there, and y is equal to x, and leaves it when y is equal to 1. Okay, so that's why we get the region interval y goes from 1 to 0. And don't forget, in this case, y can be anything between 0 and 1. Okay, so basically we drew a line here. This is the integration for x, and the y region is 0 and 1. Okay, so that gives you the limits for the integration and the fact that y should be between 0 and 1. Okay, and now it's a very similar task to what we did before. We integrate this function with respect to x between these limits. So again, this one is easy. It's x squared over 2. This is x times y. X goes between y and 1, and we multiply by 2 in the end. Okay, so this one's a bit more complicated. Some simple algebra. So you substitute x is equal to 1, and you'll get 1 over 2 plus y. Okay, minus the case when x is equal to y in here, and if you do some simple algebra, you'll get the answer 1 plus 2y minus 3y squared when y is in the set 0, 1. Okay, so that's the marginal PDF of y. Now what's the point here? What we want to see now is whether or not the random variable x and y are independent. So in order to work that out, all I'm going to do is I'm going to take this function in this range, I'm going to take this function in this function in this range, I'm going to multiply them together, and I'm going to work out whether or not the joint PDF is equal to the product for every x and y. So f of x, y is equal to this, f of x is equal to this, and f of y is equal to this. Okay, so I can easily find an x, y in this triangle. Okay, this is my support, by the way, so I can put a y value of x here and a value of y here, right here. And I can evaluate this function for x, this function for y, and this one for x and y. And it's easy to find the pair of x and y where this thing is not equal to this product. Okay, so that's the key point. I don't find the last remark particularly useful at all. It doesn't help me at all. So basically what you can do very simply, you find an x and a y value for which this is not equal to this. And it's basically true for almost every x and y. Okay, you can see that this function doesn't necessarily coincide with this product for every point in that shaded red triangle, sorry. Okay, and I'm not doing this. I read this beforehand. I find it completely useless. So I'm going to go straight to example 5. It's not that I think it's I think it's confusing, not useless. I don't think it will help us. I think that the start of the example is particularly informative. Okay, so let's have a look at this one. So this example is the joint PDF of x and y. Again, is a very familiar type of example. X 1/3 times x times 1 plus y if x lies in this interval and y lies in this interval, and 0 otherwise. Okay, so in this case, the shaded region for which the random variable, the joint PDF of x and y, is non-zero is when x lies between 0 and 2 and y lies between 0 and 1. So this is the shaded region, and then you have a z or z axis, and the function f as z is equal to this one. And then we ask the inevitable question, are x and y independent? Okay, or not inevitable, but a relatively sensible question. Okay, so this one is not so obvious, perhaps, but the things which make me suspect that it may be independent are the following. First of all, the range of x and y are independent, and this function, it factorizes into a product of a pair of functions in x and y. Okay, so I think a priori it's likely they're independent. I actually can't remember if that's the case, but I would expect them to be so before starting. Okay. So let's verify whether or not they're independent. So let's find the marginal PDF of x. Okay, so as usual, we write down the joint PDF of x. So again, I think this line here, you can ignore it. So you fix x in the set 0, 2. Okay, and then you integrate the joint PDF of x and y over the range of y. So in this case, remember the range of y is simple. It's just 0 and 1. We haven't got to do anything complicated here. So we just integrate between 0 and 1, this thing, okay, with respect to y. Okay, so x/3 is a constant, so I'm just integrating 1 plus y with respect to y, which is, of course, y plus y squared over 2, and y goes between 0 and 1. Okay, when y is 0, I don't care, so I just evaluate this function when y is equal to 1, which is 1 plus a half, and that's 3/2. So 3/2 times x/3 is x/2, and x is in this interval 0 to 2. Okay, and it's 0 otherwise, as I've stated from the beginning. Okay, and so this is looking good actually for them to be independent, because this thing looks like this got this factor x here. So let's see if it's the case for what happens to y. So the marginal PDF for y, again, we fix y in its interval, which is 0 to 1. Yes, 0 to 1. If I said x was in 0 to 2, if I didn't say it before, yeah. So y is between 0 and 1. And we integrate between the region 0 to 2, that's the region of x. x/3 f1 plus y dx, that's the joint PDF, and I'm integrating with respect to x. Okay, so now again, what do I do? Well, this 1 plus y/3 is a constant, so I can take it outside the integral, and now I'm just integrating x, and the integral of x is x squared over 2. It goes between 0 and 2, so at 0 I don't care, and at 2 I'm going to get 4/2. Which is equal to 2, so I get 2 times 1 plus y/3 when y is constrained to this interval. Very good. Okay, so you can see that it's looking very good. Okay, now if I take f of xy, that's 1/3 x 1 plus y when x and y lie in this interval. When x lies in the particular region 0 to 2, I get 1/2 x. If I multiply that by 2/3 1 plus y, I'll get 1/3 x times 1 plus y. And that's equal to exactly the density function of interest. So in this scenario, whatever x and y I take, the joint PDF is equal to the product of the marginals. So precisely the random variables x and y are independent. Okay, very good. So let's move on to example 6. So example 6, this has a joint PDF of f of xy, which looks like x plus 3/2y squared when x is in 0, 1 and y is in 0, 1, and 0 otherwise. And we're asked if x and y are independent. So again, I haven't checked, well, I've checked the notes, but I've forgotten whether it's the case. I guess that they're probably not, because this doesn't factorize into a function of x and y, but we'll see. Maybe I'm wrong. Let's see. Okay, let's look at the joint density function. So the marginal density function for x. So the method is the same. You've seen I compute the marginal for x, I compute the marginal of y, I multiply the two, and I hope for the best. So the marginal density function for x is the joint PDF for x and y. It looks like that. And now I integrate over the range of x, and x goes between 0 and 1, I believe. So that's 0 and 1, and I'm integrating with respect for x fixed in the set 0 and 1, I integrate the joint PDF over y, which goes between 0 and 1. Okay, so now I'm just integrating this function with respect to y. So this is x times y when I integrate it. 3 over 2 y squared is going to be 3 over 2 times y to the 3 over 3. Okay, so it's y to the 3 over 2. Between y 0 to 1, of course when y is 0 I don't care, so I just put y is equal 1 here, so I'll get x plus 1 over 2 when x is in the interval 0 to 1. It's the marginal PDF of x. Okay, very good. What's the marginal PDF of y? Well, it's almost the same calculation because the range of support for y and x are the same. So basically I have this. This is the joint PDF, and now I integrate with respect to x now, not y. Y is fixed in the interval 0 to 1. Otherwise we get 0, so this is not needed in line. So integrating this is x squared over 2. Integrating this is 3 over 2 y squared times x. When x is 0, everything is 0, so I don't care. When x is 1, I'm going to get 1 upon 2 plus 3 over 2 times y squared. Okay, so that's that. Okay, so now if I multiply the 2, and now if I multiply this one by this one, well, I'm not necessarily going to get this one. Okay, so the product of the marginals is not equal to the joint probability density function for every x and y. Okay, in fact, there are very few x and y for which they are true. It is they are equal. So it means immediately that the joint PDF does not have independent random variables. And again, as I explained to you earlier, one of the clues for that was, and again, I forgot, so of course I read the notes before I came in, but I'd forgotten whether they were independent or not. But my guess was based upon the fact that this does not factorize into a product of functions of x and y. So right from the beginning, I do not think that x and y are probably not independent. Okay, that's where my thinking came from. Okay, very good. So that was independence, and independence, we're going to use that quantity or that property many times in the future, I hope, or at least if I have anything to do with it, we will. Let's go on to the notion of joint expectations. Okay, so now what we do is we consider a function g, which is a function of x and y, and for our purposes we're going to assume it's real valued. Okay, so just don't think about anything vector valued. So I take a point x, I take a point y, and I'm going to get back a number. So for example, x squared plus y squared. So I don't think about vectors or anything like that, but one can easily define this notion for vector valued functions. I just don't want to get into it. Okay, so this thing is a scalar function. So the expectation of any function of a pair of random variables x and y is, as one might expect, the function weighted by its probability mass function when x and y are discrete, summed over all possible pairs of random variables x and y. Okay? Now, for the notion of a continuous random variable, it's the same thing. I take the function, I multiply by its joint probability density function, and I integrate over all possible values of x and y. And x and y could be potentially between minus infinity and infinity. Okay? And that's pretty much, if you remember, if you cast your mind back to a couple of weeks ago when we looked at expectations of functions of random variables, basically it was the same thing except when we were having just one random variable. So this is just g of x, I have f of x, g of x, f of x. Okay, so it's the obvious definition in 2 dimensions, and you can go to n dimensions, although I don't know if we do that here. So let's have a look at one special case which you may or may not have heard of, which is something called the covariance. So if I define the function gxy to be x minus the expectation of x multiplied by y minus the expectation of y, this gives you a definition of the covariance between 2 random variables. Okay, so that's what we're going to write down. I'll explain to you what it means in a little bit more depth in a moment. But suppose you're given a pair of x and y random variables bivariate with joint PDF or PMF, f of x, y, then the covariance of the pair of random variables is defined to be the expectation of x minus mu x multiplied by y minus mu y. Okay, so let me just say what this thing means. So basically it's a measure of the strength of dependence. Okay, so big covariances relative to small covariance indicate that x and y are somehow more dependent on each other. And they really tell you about the sign of a correlation between these random variables as well. Okay, and I'll tell you what correlation is in a moment, but it's just a measure of dependence. big absolute values tell you that the pair of random variables x and y for four random variables on the same scale, bigger covariances mean more dependence, roughly. That's what it means. What is the expression for this? So in the discrete case, we just substitute g into our definition for expectations of functions of pairs of random variables. So if x and y are discrete, the covariance is simply x minus the mean, which is, remember what mu of x is, the expectation of x, is the sum over all x's of x times the marginal PDMF, P, probability mass function of x, fx of x. Similarly, this one is the sum over all y's of y times fy of y. Okay, so this is the covariance. That's exactly just using or mimicking exactly this formula for the special case that g of xy is as given. And in the continuous case, as you can see, it's x minus, it was the same thing really. You just substitute g of xy into your expression, which is just basically, this is g of xy. This mu of x is the integral over all x's of x times the marginal density on x, integrated with respect to x, and similarly for y. And this is the joint PDF. Okay, so this is how you formally compute the covariance for pairs of random variables. And as I say, it's a measure of dependence. That's really the best way to think of it. And basically, it's going to help us in calculating correlations. Okay, so these are some formulae which you can remember. I may derive these for you tomorrow, actually, since it seems that we're going very fast. So there must be something else we can learn. So the covariance of x and y, you can show it, and I think I will show these things. Not today because I haven't prepared the lecture for that, because I thought it would be more challenging than I was expecting, and it's not. So we have the covariance of x and y. You can show that it's the same as the expectation of x times y minus the mean of x minus times the mean of y. In fact, generally when you're computing the covariance, you're going to use this one rather than using this one, because basically normally this is just a little bit easier to work with. Okay, now you can show, so the independent, if x and y are independent, the covariance of x and y is precisely 0. Okay, so why is that the case? Well, basically it comes from the fact that if you look at this expression, so the expectation of x and y is what? Well, the expectation of x and y is the integral over all x's and y's of x times y times the joint PDF of x and y. Right, but we are saying something very special. X and y are independent, right? So remember, what does x and y independent mean? We've had 6 examples today, so we must not forget what that is, right? That is, and I will just show you, the joint PDF is equal to the product of the marginals. Okay, so what am I talking about? Well, the expectation of x times y is equal to the integral, double integral of x times fx of x times y times fy of y, integrated with respect to x and y. So basically this, the expectation of x times y is equal to the expectation of x multiplied by the expectation of y because of this property. And so what that means is that independent random variables have 0 covariance. That's what the property says, and I've explained to you why that is the case. But it's important to note that it doesn't go the other way around. Just because a pair of random variables have 0 covariance does not mean that x and y are independent. For example, this thing being 0 could just be by chance. It just happens to be that we have certain numbers which go into our equation and we end up getting 0, but it doesn't necessarily mean that x and y are independent. So it's important to remember that x and y being independent gives you this. This does not go the other way. If I tell you this, it doesn't mean x and y are independent. You can find pathological examples where where that is the case, that the covariance is 0, but actually it turns out that x and y are dependent. The covariance, so if you take a linear combination, so this is interesting. So you take the covariance of a times x plus b. So here a is a constant, b is a constant, c is a constant, d is a constant. So I take the covariance of linearly transformed random variables x and y. You can show that the same as you ignore a and b and d, and it's just the covariance a times c times the covariance of x and y. So this is basically tells you something about the fact that the covariance of x and y is something related to linear random variables, a linear type quantity. Okay, so basically if you know the covariance of x and y, you know the covariance between any linear shift and scaling of x and y. Okay, you can verify this formula. Again, I'll write down a worksheet and we can have some fun with it tomorrow, depending on whether I think it's worth it. Similarly, you can show for any pair of random variables a times, so I take x and y, they're jointly defined, I multiply them by a scalar constant, and I compute the variance, so the variance of a sum of linear combination of random variables. And it turns out that the variance of a linear combination of random variables is precisely equal to the square of the constant of the variance of x plus the square of the constant b times the variance of x plus 2 times ab times the covariance of x and y. Okay, and again, we can verify these formula, but let's take them as being for granted right now, and I will write down the proofs for you if you like, for you tomorrow. Okay, let's have a look at the correlation coefficient. So the covariance is really intrinsic for the correlation coefficient. I'm fairly sure, you all being very quantitative students, that you've heard of what the correlation coefficient is. Formally, mathematically, we define it in the following way for random variables which are non-constant. Okay, constant random variables are not important here. And it's devoted by, one use rho xy. And that's the covariance of x and y over the square root of the product of the variance of x times the variance of y. Now, what is the correlation coefficient, or correlation really? Well, first of all, one can verify that the correlation is a number which is at most 1 and less than or equal to minus 1. So what the good thing about correlation the notion of a correlation coefficient is the fact that one can use correlation to compare dependencies of random variables, because it's on an absolute scale, right? I can say that x and y, if they have a correlation 0.1, are less dependent than pairs of random variables of a correlation of 0.7, for example. But it's a specific measure of dependence because it measures dependence which are linear, okay, between x and y. So that is to say, so basically what it means, if the correlation coefficient, for example, is 0.7, what it means is between x and y, roughly means is that as y goes up, x goes up, and there is a distinct linear relationship between them. And similarly, if x's correlation between x and y is minus 0.7, if y goes down, x goes up, and vice versa. Okay, so it's really telling you linear relationships. It doesn't tell you this is what, well, okay, let me just go to the next point. So the next point is if x and y are independent, the correlation is 0. Why is that? Well, that comes from the definition. The correlation coefficient is this, okay, and you have the covariance. And remember that if x and y are independent, the covariance is 0. So the covariance is 0, the correlation coefficient is 0. So if x and y are independent, then the correlation is 0. However, independent random variables have 0 correlation or uncorrelated, but uncorrelated random variables are not necessarily independent. And why is that? Because basically, although I haven't really explained it, basically this is a measure of linear relationship. Okay, so if x goes up and y goes up and the correlation coefficient is positive, i.e., then that's linear. But that just because the correlation is 0 doesn't mean the random variables have no dependence. There could be, for example, quadratic, cubic, non-linear relationships between x and y which force them to be dependent. Okay, so it's important to note independent random variables have 0 correlation. Uncorrelated random variables, i.e. random variables with 0 correlation, are not necessarily independent. And there are pathological examples. I think the level of where we're at, I can't give them to you yet, but perhaps in the next chapter we will. Okay, let's have a look at an example. Excuse me. So let's have a look at an example. So this is an example 1, section 3.3.2 on page 3, chapter 347. Let's believe these notes. Looks familiar. So this is the joint distribution of a pair of random variables x and y. So x can take the value of 0 and 1, y can take the value of 0, 1, 2, 3. This, for example, this is the probability that y is 1, x is 0. This is the probability that y is 3 and x is 0, and so on and so forth. So then we sum these numbers, we get the marginal of x. Sum these numbers, we get the marginal of x. We sum these numbers, we get the marginal of y, and so on. Okay, very exciting. Right, and we're asked to compute the following things. So we want to look into our special type of relationship. We want to compute the expectation of the difference, y minus x, and the covariance of x and y, and we'll worry about C and D when we get there. Okay, The expectation of y minus x is straightforward. Basically what I have, if I have 8 values, right, 8 possible values, so I do, for example, 0 minus 0 times an eighth, which is obviously 0, and for another one, we do 1 minus 0 times a quarter, it's y minus x, importantly, 2 minus 0 times an eighth, 3 minus 0 times 0, 0 minus 1 is times 0, 1 minus 1 times an eighth, 2 minus 1 times a quarter, 3 minus 1 times an eighth, and we add those numbers together. Okay, that's what this thing is doing here. And if you do that, that gives you 1. Okay, not very exciting, but I think hopefully illustrates the notion of computing expectations of pairs of random variables. If you prefer the expectation of y minus x, you can very, very easily show that's equal to the expectation of y minus the expectation of x. And then, apparently, the expectation of y is 1.5 and the expectation of x is 0.5. That's another way of doing it. In fact, it's almost the same thing. I mean, if you know these things, then you would just have this one for free. Okay, so we're part B. We want to find the covariance of x and y. This is our first attempt at it, so let's spend some time. So remember that the covariance between x and y is the same as the expectation of x times y minus the product of the expectation of x and the expectation of y. So let's start with the expectation of x times y. Okay, this expectation of x times y, all we do is we multiply x times y by their respective probability and add them for all possible x and y. So for instance, the quantity of interest is going to be 0 times an eighth, 1 times 0 times a quarter, in fact 2 times 0 times an eighth is 0, 3 times 0 times 0. So okay, so this thing I don't care about. And this one I don't care about here. So then 1 times an eighth, 2 times 1 times a quarter, and 3 times 1 times an eighth, and we add those three numbers together basically. So the expectation of x times y, as you can see most of them are zeros, I get back 1. The expectation of x, well, we know how to compute that. Let's remind ourselves the expectation of x is going to be 1/2 times 0 plus 1/2 times 1. Okay, so that should be 1/2. Right? The expectation of y is 0 times an eighth plus 1 times 3/8 plus 2 times 3/8 plus 3 times an eighth. Okay, it should be 1.5, I think. Yes, 1.5. So the covariance between the random variables x and y is 1 minus 1/2 times 3/2 is equal to a quarter. Okay, remember covariances, they can be positive or negative, so that doesn't help you if you get a positive or negative number. It's not like variances, for example. Variances have to be positive, covariances are sign indefinite. Okay, question C. So now we want to find the correlation. So the correlation is not too bad because we've got the hard part somehow, we've got the covariance. So we just need the variances of x and y. So the variance of x, remember, is basically going to be the expected value of x squared minus the expected value of x all squared. So here, this is the expectation of x with 0.5 and I square it. Okay, so that's where this minus part comes from. And this one, well, that's basically going to be what? Well, it's x squared, so it's 0 times 1/2, I don't care about that, 1 squared times 1/2. So we're going to add 1/2 minus 1/2 squared. So the variance is going to be at 0.25. To compute the variance of y, so again, we have, this is the expectation of y squared, this is the expectation of y all squared, because remember the expectation of y is 1.5, so I subtract 1.5 squared here. So this is going to be the expected value of y squared, which is going to be basically, I'll just read it out for you. So the expected value of y squared is going to be 0 squared times an eighth, plus 1 squared times 3/8, plus 2 squared times 3/8, plus 3 squared times 3/8. Okay? So that's what we're doing there. So that happens to be 3/4. Okay, so now we're in a good position. We know the covariance, we know the variances, so that's basically going to give us an answer. So the covariance was 0.25, so we have positive correlation, at least, over the square root of 0.25 times 0.75. That happens to be apparently 1 over square root of 3. Okay, very good. So this is our final part of the question, the example, and we have the bar break. So now we want to compute the conditional expectation of y given x is equal to 1. I think we computed the conditional PDF. So this one, so if you look at chapter 3, page 49, something we probably looked at on last Friday, the conditional PMF of y given x is 1 looks like this. Okay, I think that we did that I'm pretty sure we did that before. So the expected value of y given x equals 1 is going to be 1 times a quarter plus 2 times a half plus 3 times a quarter is 2. Okay. And that's the end of the example. Okay, so let's have a break. We'll break for 5 minutes. Okay, so let's resume. Okay, so we're still on this correlation and covariance stuff that we're talking about, and now we're looking at this example, our example that we saw, example 3. Well, anyway, we saw this earlier today. So we have a joint PDF of a pair of random variables x and y on a rectangle where x is between 0 and 1, y is between 0 and 2, and it has this joint PDF. Which looks like this, 0 otherwise. We're asked to compute the covariance of x and y and the conditional expectation of y given x is a half. I think we have the conditional PDF, by the way. That's something that we computed back a few days ago. Okay, so now we do the covariance. So to compute the covariance of x and y, we need to compute the expectation of x times y. So the expectation of x times y is simply x times y times the joint PDF integrated over the range. So x goes between 0 and 1 and y goes between 0 and 2. X times y times, and this is the PDF. Okay, and we just have now an integration task. There's nothing more than that. So now what we do is we integrate this function with respect to x. So the y doesn't matter, so I have x cubed. X cubed integrated is x to the 4 over 4. This one I have x squared. So x squared is integrated to x to the 3 over 3. And so I have a factor of 3 there, so I get 9, and of course I have the y there and the y there, so that's y squared. So that's my integral with respect to x. And we note in the case when x is 0, of course that knocks the whole thing out, so any curve when x is equal to 1. So when x is equal to 1, I get y over 4 plus y squared over 9, and I integrate with respect to y. The integral of y over 4 now is y squared over 2 times 4 times 8. Plus y to the 3 over 3 times 9, which is 27. Okay, and y goes between 0 and 2. So again, when y is 0, I don't care, and y is equal to 2, I get 2 squared over 8 plus 2 to the 3 over 27. So apparently 43 over 54. Okay, so that's the expectation of x times y. I think we have the marginal PDF of x. So this was the marginal, yeah, in fact we have done this calculation today. So this is the marginal PDF of x. So to find the expectation of x, all I do simply is I take x times the marginal PDF of x and I integrate it over the range where x goes between 0 and 1. Okay, so now I have, and note that remember we said that x and y are not independent, so I'm not going to get 0 at the end. So now I'm integrating 2 times x to the 3, which is 2 times x to the 4 over 4. Plus 2 over 3 times x squared, that's integrated to x 2 over 3 times x to the 3 over 3 is 2 times x to the 3 over 9. And x goes between 0 and 1, so again when x is 0 I don't care, and x is 1 apparently I'll get 13 over 18. So that's the expectation of x. The expectation of y. The expectation of y goes between 0 and 2, that's the range of y, I have y, and this is the marginal PDF of y. I'm pretty sure we did that today as well. Okay, so now I'm integrating y over 3. That's y over 3 is y squared over 2 times 3 is y squared over 6. Y squared over 6 integrated is y to the 3 over 3 times 1 over 6 is y to the 3 over 18. Y goes between 0 and 2. At 0 I don't care, and when y is equal to 2 I get 2 squared over 4 plus 2 to the 3 over 18. So I get 10 over 9. Okay, so the covariance of x times y, f x and y is the expectation of x times y minus the expectation of x times the expectation of y. This was the covariance. This, I believe, is the expectation of x. This is the expectation of y. And so we get a covariance which is minus 1 over 62. Now what does this mean? Well, basically what this means is it's very close. These random variables are very, very negative. They're negatively correlated. And it's possible that that negative correlation is close to 0. I'm not sure yet. We would have to compute the variances. But at least this is going to imply immediately the correlation is negative. That means if x goes up, y goes down. That's what it means. Okay, so that was part A. Part B is asking us to find the expectation of y given x is equal to a half. Okay, so the expectation of y given x equal to half. So this is a joint conditional PDF, and this is a conditional distribution. It's a conditional density actually of y given x, and this was something we derived apparently on chapter 3, page 58. Okay, so now to compute the expectation of y given x is equal to half, all I need to do is I multiply this thing by y and I integrate it over the range of the conditional PDF. Okay, and that's what I've done here, or we've done here. Okay, so this is straightforward. You can take the factor 1 over 10 outside. You get 3 times y, integrate 3 times y, you get 3 times y squared over 2. And now I've got 2 times y squared. I integrate that as 2 times y to the 3 over 3. Okay, y goes between 0 and 2. If y is 0, it's 0, and y is 2, I get 3 over 2 times y squared plus 2 times 2 to the 3 over 3 times 1 over 10 gives me 17 over 15. Okay, and that's at the end of chapter 2. 3. Chapter 3? Okay. So that's chapter 3. We're going to see a little bit about chapter 4. In fact, I've prepared some additional notes because we're going very fast. I assume there must be more to this course than this. So unfortunately, I have to wait for me to get to my alumni. There we go. Let's see. Let me get this extra thing because I was a little bit slow. So give me a moment. Sorry. What is my user ID? Do you have to do this like this? Sorry, give me a moment. This is not very exciting for you. It gives you a chance to zone out. Sorry about that. Okay, very good. So this is sure that you've all had a very exciting time accessing this. So this new file, we're going to talk about it in a moment, I hope, because it's supposed to say binal mean. It says meme, but sorry about that. Anyway, I want to download it. Okay. This one is fine. Alright, so this is a file. We're going to see it in a moment, I hope. Okay. So this is chapter 4. So what is this all about? Chapter 4, it's called Special Probability Distributions. Now what it is that there are types of probability distributions for discrete and continuous random variables which are catered to particular scenarios. Okay, and in particular the discrete case where one has a kind of nice interpretation of various PMFs. Okay, in fact we could have done this one before we did chapter 3 actually. It's funny to do it this way. So discrete distributions, so you can see a lot of discrete distributions. Some we've seen before, so the discrete uniform distribution we have seen it already, but we're going to talk about it. The Bernoulli and the binomial distribution is something we're going to discuss later today, I hope. Well, we've got plenty of time, so definitely. And this one, in fact I have a special note for this as one, we're going to talk about that. And we will talk about these things as we go along. But the discrete distributions are kind of quite nice and rich. They're all developed for different types of scenarios, and it's important to understand where each one is relevant. The continuous distributions are kind of a little bit less, they're less prevalent. I mean, we're only going to see 3, the continuous uniform distribution, which I think we've already seen. The exponential distribution, we have certainly seen even today, and the Gaussian distribution, which if you have not seen before, you have heard of it, because the normal distribution or Gaussian is well understood. So by the way, if I say throughout this discussion normal and Gaussian, they mean the same thing, because it was Carl Friedrich Gauss's distribution. So I call it Gaussian or normal, it doesn't make a difference to me. And then this is all about approximations, so we'll talk about that eventually. Okay, so what these distributions are all about is they are catered for a specific scenario, and I'm going to describe, first of all, the most basic one that we have seen. For example, it's relevant when you're rolling a die or flipping a coin. Okay, so a random variable x is a definition, I suppose you could call it a definition. So a random variable x is discrete, so it can take a countably infinite number of values. In this case, it's exactly finite number. So this is a finite distribution over a finite number of points. Okay, so it takes the values x1 up to xk. K is finite. Okay, and it takes them with equal probability. You cannot have a uniform distribution on a countably infinite domain because it cannot sum to 1, by the way. So the random variable is said to be discrete and a discrete uniform distribution if the probability mass function, I call it probably mass function, is given by fx of x and it's equal to 1 over k for every x in the set x1 up to xk. And 0 otherwise. So what it says is every point in the sample space, x1 up to xk, every point that to support the random variable, has equal probability. Okay, and it's a nice formulation for certain types of cases, such as coin flipping is an example of a discrete distribution, which is uniform, rolling a die, fair die, and so on and so forth. Let's look at some examples. theorem. Okay, I wasn't called the theorem, but okay. So the mean of a random variable which is discrete and uniform is as follows. So the notations are changing all over the place, but this thing mu is mu subscript x, you've seen today. It's the expectation of x. So this is an exchangeable notation, so just as one of your colleagues mentioned that a moment ago, this is exchangeable. So the expectation of x is the sum over all possible x's of x times the marginal, or here it's only one random variable, so this is just a random variable fx of x. And that's equal to what? Well, basically the random variable x can take the value x1, x2, x3 up to xk, so I can take the index, the sum I is 1 to k of xi, and the probability that xi is equal to the probability of taking the value xi is 1 over k. So the mean is just the sum of the xi's times 1 over k. That's the average value of a continuous, random, discrete, uniform distribution. This is nothing, I mean, it's not a theorem, but anyway. The variance of x happens to be equal to this. It's basically x minus mu squared. Okay, so this is the definition of the variance. Okay, that's the expected value of x time minus the mean all squared multiplied by this probability mass function. Okay, this is the sum over all possible x's. It's a kind of funny notation here. Okay, so this sum is equivalent to basically x takes the value x1, x2, x3, x4 up to xk. So I can take my sum from i is 1 to k of xi. Okay, that's the value of x. Minus mu all squared, and the probability that I take the value x is 1 over k. Okay, so that's the variance. If you prefer, we know that the variance is equal to the expectation of x squared minus the mean all squared. Okay, so the expected value of x all squared is basically the probability that x is equal to x, right, because that comes outside, times xi squared. That's the sum over all x's of the x's, minus mu squared, which we calculated here. Okay, let's have a look at an example. This is an example of a discrete probability distribution which is uniform. So, we have a light bulb. It can either be randomly selected from a box which has a 40, 60, 75 and 100 watt bulb. Okay, so each element in this sample space, which is 40, 60, 75, occurs with probability 1 over 4. So this is a discrete uniform distribution where fx of x is equal to a quarter if x lies in the set 40, I'm talking about this part, 40, 60, 75 or 100, and 0 otherwise. It's an example of a discrete uniform distribution. Okay, not very exciting. The second example is the one we have seen almost in lecture 1, which is the notion of rolling a fair die. So if you roll a fair die, the possible outcomes are 1, 2, 3, 4, 5, 6, six-sided dice, and each of them are equally likely with probability 1 over 6. So this again is a uniform distribution. fx of x, the second bullet, is equal to a sixth where x lies in the set 1, 2, 3, 4, 5, 6. You get 0 otherwise. We know the expectation of x. There's nothing exciting to say there. It's just the sum x1, x plus x2 plus x3 plus x4 plus x5 plus x6. Xi is equal to I in this case, multiplied by the probability 1 over 6, I get 3.5. And the variance, okay, the variance is all very exciting. Remember that's the expected, well the variance, remember we have the expression in this theorem, it's 1 over 6 times the sum I is equal 1 to 6 of xi, which is I, minus mu, which is 3.5 all squared. Okay, and that's what you're doing. 1 minus 3.5 squared plus dot 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 plus 6 minus 3.5 squared times 1 over 6 happens to be 35 over 12. If you want, you could do it in a different way. So the mean is 3.5 squared. The mean is 3.5, so you get 3.5 squared. And the expected value of x squared is 1 over 6 times 1 squared plus 2 squared plus dot 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 plus 6 squared. That's obviously the same value as we had before. Okay, and the discrete uniform distribution is one which we, as I said, we were able to kind of see almost from lecture 1. But another example of and perhaps the more interesting one is this notion of the binomial or Bernoulli distribution. The Bernoulli is basically a special case of the binomial. Okay, so a Bernoulli trial, he calls it Bernoulli experiment, but I'm going to say Bernoulli trial, it's the same thing. It's just an experiment and it's got two possible outcomes. So we can basically have a random variable, let's say it can take the value 0 or 1, and it takes 0 with some probability and 1 with the probability, 1 minus the other probability. Okay, so it's only got 2 possible outcomes. Success or failure, boy or girl, head or tail, whatever, yes or no. It's 2 values. It's 0, 1, you can think of it just being a 0, 1 valued random variable. Okay, we just code 0 and 1. So for example, the easiest way to think about it is success or failure. So we say failure is 0 and success is 1. So we can say success with probability p, and then failure with probability 1 minus p. And that's it. And p is a number between 0 and 1. It's a probability. This is what we say here. So we make the definition. So a random variable is said to have a Bernoulli distribution if the probability mass function of x is given by this. So fx of x is equal to p to the x times 1 minus p to the 1 minus x, where x can be 0 or 1. Okay, so basically p is a number between 0 and 1. It reflects the probability that x takes the value 1. Okay, so the random variable x is only 0 or 1. It's 0. This function is defined to be 0 otherwise. So sometimes people write 1 minus p is equal to q. I don't see it very complicated to write p to the x, 1 minus p to the 1 minus x. It doesn't make a difference. But the probability x is equal to 1 is p, and the probability x is equal to 0 is 1 minus p is equal to q. Okay? It's one of the most, I think this is basically one of the most simplest probability distributions you can see, really. Okay, let's look at some remarks. So f sub x of x depends on a quantity that can be assigned any one of a number of possible values, with each different value determining a different probability distribution. That's basically what this sentence is rather mystifying, but what it really means is that basically there's a family of probability distributions, right? Once you specify p, that specifies the probability mass function of the random variable x. So this is a family of probability distributions, and the associated number p is called a parameter. So this is our first example, at least in this course, of a parametric probability distribution, and its parameter is p, where p is a number between 0 and 1. We don't take the value 0 or 1. It's a silly thing to do, because if p is 0 or 1, the whole thing is deterministic. We know what's going to happen. So of course we constrain it to be in the open interval 0 to 1. Okay. So this is basically because the collection of all probability distributions for different parameters are called the family of probability distributions. Okay, so I started with that because I think it makes more sense, actually. Okay, so that's it. Okay, the expectation. So this is a theorem. Do we have the proof of it? No. We can talk about this. So the expectation, so there's a theorem 4.2. There are no proofs here, but I can at least tell you the proofs. I'm going to do the proof of the binomial case, which is the next thing in this slides. So if x is a Bernoulli, then the mean of x is p. Okay, so the expectation of x is p. Now how can you verify this formula? It's very straightforward. Right, we'll start with this. So basically the expectation of a random variable with this Bernoulli distribution is the sum over all x's of x times this formula. Okay, but x only takes 2 numbers. It's very easy, right? So I take x is 0, I don't care. Okay, because it knocks this whole thing out. Plus the case where x is 1, so I get 1 times p plus 1 minus p to the 1 minus 1. So I basically have the expectation of x is 1 times p, so it's p. Okay. That's simple. This calculation is simple because I'm only summing over 2 numbers. The variance, so the expectation of x is p, so the expectation of x all squared is p squared, so I just have to compute the expected value of x squared. Okay, so the expected value of x squared is x squared times the probability mass function summed over all possible values of x. So if x is equal to 0, 0 squared times this doesn't matter, we don't care. If x is equal to 1, x squared is equal to 1. So 1 times p to the power 1 times 1 minus p to the power 0. So the expected value of x squared is equal to p. So what is the variance? The variance is equal to p minus p squared. So p minus p squared is p minus p times 1 minus p. It's p times q if you like, but p times 1 minus p is enough. So you can compute the expectation of the variance, and in this case, because there are only 2 sample points in the sample space, there is nothing really clever to be done, because basically you're just adding 2 numbers to 2 expressions together, so there's nothing that you need to worry about. Okay, so a box continue contains 4 blue and 6 red balls. If a red ball is drawn at random from the box, what is the probability that a blue ball is chosen? Well, this one we don't need anything interesting, but we can encode this as a Bernoulli random variable. So if we take the case x is equal 1, is success, i.e. we get a blue ball, and 0 otherwise. Now the probability we get a blue ball, we're choosing at random, we have 4 blue, 6 red, so the chance I pick a blue out uniformly at random is probability 4 over 10. Okay, so the probability of success in this Bernoulli trial is 4 over 10. Okay, the probability I don't get a blue ball is 1 minus 4 over 10 is 6 over 10, 0.6. And so basically this is the probability mass function. Okay, and the case, so this case is a special scenario of the Bernoulli distribution, the case p is equal to 0.4. Okay, it only takes 2 values. So this expression here is equivalent to this expression here in the case p is equal to 0.4. Okay, I prefer to write this one because it's faster to write down, but equally if you like you could write down this, it's the same thing. Okay, example 2. So example 2 is a little bit funny actually, but anyway, so we have a sequence of Bernoulli trials. Okay, so Bernoulli trial 1, Bernoulli trial 2, Bernoulli trial 3. Okay, so now we have the sequence of Bernoulli trials and we perform them several times independently. So this is a sequence of independent and identically distributed Bernoulli trials. So I have Bernoulli trial 1, then the random variable, so that's the random variable x1. So now random variable x2 is a Bernoulli trial, has a Bernoulli distribution independently of the first. The third one is a Bernoulli trial x3, and it has a probability distribution which is independent of the first and the second, and so on and so forth. All the random variables are independent and of identical distributions. Okay. Now consider a box that has 4 blue and 6 red balls. 5 balls are drawn from the box one at a time. Without replacement, I think they should say. Okay, so let the draw of the blue ball is success. Now we have 5 Bernoulli trials. Well, yeah, with replacement. Sorry, yes, with replacement. So now we have basically, now we do that. So we start with our box. We have 4 blue, red balls. We take out a ball. Okay, that could be blue or red. We put it back. We do that 5 times. Okay, so we they're supposed to be independent. So we suppose that the draw of a blue ball is success. So we know that the probability that on any of these given trials is 4 over 10 because we're replacing the ball after we've taken it out. Okay. Now let's consider, what was it, n. Okay, that's 5. Okay, yes. Okay, that's a sequence of 5 Bernoulli trials. Okay, all very exciting. So I haven't learned anything yet. Let's consider now the case where you have n Bernoulli trials that are independent. So x1 is the result where you get 0 or 1 from the first trial. x2 is the result of the second trial, and so on. And we will consider n of these trials which are independent of each other. Okay, so so if I want to write down the joint PMF of x1 up to xn, that's the product of the probability mass function for x1 times the probability mass function for x2 times the probability mass function for x3, all the way up to the times the probability mass function for xn. Okay, if you're wondering what am I talking about, as you may think I'm going mad, but I'm not. What I'm talking about is where we started basically today. So I think that's page 84, something like that. So what I mean is that basically I'm talking about this thing. So in the case that I'm talking about, the probability mass function for x1 is a Bernoulli distribution, so it's a PMF which is p to the x1 times 1 minus p to the x1. This one is going to be p to the x2 times 1 minus p to the x2. They're identical. Okay, so the probability of each distribution p is the same. So that's the joint probability mass function for those random variables. Okay, each is like that. Okay, so still I haven't told you anything. Okay, we're still here. Now we define, perhaps confusingly, capital X as the total number of successes. So what that means is that basically in these n Bernoulli trials, so X represents precisely x1 plus x2 plus xn. Okay, so for example, x1 could be 1, x2 could be 1, x2, 3 could be 0, so on all the way up to xn minus 1 could be 0, and this is 1. Okay, so that's a realization of a particular value. So this random variable capital X is scalar. It could be 0, because in the case that all of the x's are failures, x1 up to xn. It could be n, in the case that all of the xi are successes. So it's a random variable, could be 0, 1, 2, 3, 4 up to n. Very exciting. Now what we're going to do is we're constructing now the joint probability mass function for capital X. Okay. Now there are a couple of ways to do it, but we're going to do it the easy way. There's a harder way of doing it, which obviously we're not going to do. Well, actually there's another way, but anyway, it doesn't matter. So let's think about what is the probability mass function for capital X. Okay. So the probability mass function for capital X, okay, can take a value 0, 1, 2, 3 up to n. But basically it's going to consider a particular realization where we had x successes and then if we have little x successes, we have n minus little x failures. Okay. Now the probability of these x successes will have success. So if the first one has probability p, the next one, this has probability p, and this one has probability p. So this basically is the probability that this occurs is p to the power x. The probability that this occurs is q to the n minus x. Okay. But this is for a given sequence of x failure. This is basically I succeed x times in a row, and then I succeed n minus x times in a row. So the probability of this particular sequence is p to the x times n minus x. But of course, for a given little x, there are different orders in which you can obtain x successes and n minus x failures. Okay, so this is any other sequence with x successes and n minus x failures. Okay, which is different from the one we just talked about. So this is a particular sequence. I have x successes, first time success, second time success, x time success, and then suddenly something goes wrong, I get n minus x failures. And these are all independent, so basically the probabilities of all of this particular collection of events is precisely like this. But if I had a different ordering, suppose I went success, failure, and I did that all the way until I got x successes and n minus x failures if I could. Okay, it still has that same probability, right? So to give you an example, let's say we have 3, right? With 3 trials, x1, x2, x3, right? I can get failure, success, failure. That's one way to get one success. I could get success, failure, failure. I could get failure, failure, success. So the chances of those 3 events which have precisely one success are the same. The probability I get 1 success and 2 failures is p times 1 minus p times 1 minus p, and there are 3 ways of doing that. So in this case what we're doing is the number of x, so we have n Bernoulli trials and we're going to have x successes. So the number of ways of having x successes from n trials, well we already know that's n choose x, right? That's the thing that we had before. We don't care about the potential permutation, right? We just get with n things and we take x of them, and we want to know the number of ways we can take x from n without caring too much about the order. That's n choose x. That's something we learned in week 1 already. So basically now the question is, what's the probability that the total number of successes is x? So the probability that the total number of successes of x is going to be the total number of ways it can happen, n choose x, multiplied by its probability, which is p to the x times 1 minus p to the n minus x. Okay, and x could be 0, 1, 2, up to n. So for example, in case x is equal to little n, we know there's only one way to get all successes, and that's going to be p to the power n. If x is equal to 0, they're all failures, we know there's only one possible way to do that. That's going to be 1 minus p to the power n. And then, of course, for any other type of sequence, there are a different number of ways to get a total number of successes, which is 1, 2, 3, and 4, and that happens to be n choose 1, 2, 3, 4, depending on the case. It's more as an example. It's more a construction. So this is a way you construct what is called the binomial distribution. So this is the definition, and we're going to... Okay. We're coming close to what I wanted to talk about, actually. We'll see if we'll get there. So a random variable x is defined to have a binomial distribution with two parameters, n and p. So n is the number of Bernoulli trials which are independent and identically distributed. Okay, and p is the probability of success of that Bernoulli distribution, and that probability mass function has to have the form f sub x of x, which is n choose x, the number of ways I can draw x from n when I don't care about the order, times p to the x times 1 minus p to the n minus x, where p is a number between 0 and 1. So critically, as I said, it's very important to understand what this distribution is useful for. So I'm trying to highlight that in blue, but it's the very bottom line which is highlighted in purple for your benefit. So it's the number of successes that occur in n independent and identical Bernoulli trials. It's very important they're identical. If this number is different for the sum of the Bernoulli trials, you get something which looks different. So the missing word there is identical. They're independent and identically distributed Bernoulli trials, and it's the number of successes. So it's defined precisely. The definition of this random variable is here. All right? X, the random variable, which is the total number of successes, is the sum of x1 plus dot 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 plus xn, where x1 is Bernoulli with parameter success p. Independently of all other random variables, x2 is Bernoulli with parameter success probability p. x3 is Bernoulli, independent of all random variables, Bernoulli with success probability p, and so on. Okay, that is an important point of this construction. So this is an alternative definition for this thing. Okay, if you give me this, okay, and you tell me about this, this information here, that defines the binomial distribution. Alternatively, this also defines a binomial distribution. I prefer the construction that we started with because that is constructive, whereas this doesn't tell you anything. You don't know. It's just a probability mass function. Okay, we're going to see some calculations in a moment. So the case n is 1. Well, the case n is 1 is clearly just the Bernoulli, right? Because by definition, if n is 1, x is equal to x1. x1 is Bernoulli distributed. So of course, x and x1 have the same distribution by definition. Okay, so if you talk about a binomial, you get the Bernoulli in the case n is 1. Okay, it's clear because we have constructed it in that way. We can also look at you can look at the graph. This is a probability mass function for a binomial distribution. Here n is 10 and p is 0.2. Okay, so clearly because the probability of success is relatively low, of course the probability that we're having values which are low are more likely than those which are high. Okay, here we have 0.5, so again we're closer to the average value. You might think is maybe half the time we get success. Okay, this is what you might think. And here the probability is high, so again we're more likely to get higher values of this binomial random variable. Okay, so this is what I wanted to discuss. We have these additional calculations. I'm going to show you something, maybe not so exciting, but anyway. So the theorem, which is not proved in the notes, I don't know if we do it later because I didn't write the notes. But so we suppose x have a binomial distribution with parameters n and p, and we use this notation x tilde, which means distributed av, b, which we're going to use binomial, n is the number of Bernoulli trials, and p is the successor probability for each Bernoulli trial. Now it turns out that the mean of a binomial distribution is n times p, okay, and the variance is equal to n times p times 1 minus p. Okay, now what I'm going to do is I'm going to show you the proof of this result from the definition, and the proof of this result from the definition is a little bit tedious, but just to show you that you can do it. The easiest way to derive this result, and I will do that tomorrow, so basically what I'm going to do is I'm going to prove this result and then we're going to stop, but the easiest way to verify this result and this result is straight from this thing, right? I know immediately the expectation of x is the expectation of x1 plus dot 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 plus xn. The expectation of x1 plus dot 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 plus xn is the expectation of x1 plus the expectation of x2 plus dot 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 plus the expectation of xn. The expectation for any of the xi's is p, so the expectation of x is n times p. It's clear. But if you wanted to do it very more difficultly, this is what you would do. Okay, so what we're going to do is to compute them. These ones are new notes. I did them myself today just to show you that life is not always trivial. So here, this is on, as I say, so I just downloaded it from Lumnus. You can have a look over these results. I'm just going to go through these calculations a little bit. I understand that this is a little bit more different. This is actually how I used to run my course when I did ST334. It was a lot harder than this. So you can see that probably you're happy we did this version. So what we wanted to show, the expectation of x is NP. I tried to copy the notation of this course as much as I can. I'll try and make this. Can you read this at the back? Is it okay? Yes, okay. All right, thanks. Okay, so x is the expected value of x is NP. X is distributed binomial. Number of successes n, and P is the probability. And I'm going to suppose n is at least 2. The case n is 1, we have done it already. It's the Bernoulli. Okay, so I want to compute the expectation of x, and I told you, and I've already verified it through words, although I didn't write it down. The expectation of x is n times p, and you can use the definition. Another way is, of course, you can use the definition through the sum of Bernoullis, and that's the best way, really. You can alternatively use the exact definition, which is the expectation of x is the sum over all x's, so x goes from 0 to n of x times the probability mass function. This is a probability mass function. Okay, and you can see already, I mean, if you look at it, I mean, we were going to finish the calculation at the end, but you can see already it doesn't look like a standard sum. So you have to do some work here. So the thing that we did already was to do the linearity of expectation of basically independent Bernoullis, and that's the best thing to do. But if you don't want to do that, this is one alternative. So how do you do this calculation? Right, so first of all, we note that if x is equal to 0, this is 0, so we don't care about the x is 0. So we change the summation. It doesn't go from 1 to n. It's the same as when I'm going from 1 to n instead of 0 to n. Okay, that's the first thing we do. Now this binomial coefficient, remember what it is. It's n factorial times n minus x factorial times x factorial. But x over x factorial is x minus 1 factorial. Okay, this part here I haven't changed it. Okay, right, now what do I do? Right, well what I do now, what am I trying to do now? So if you look at this thing, I don't really know how to do the summation. It's not very obvious from the beginning. Okay, what am I trying to do with this calculation? It's not so important that you do this, right? This is much harder than you see for most of the course. What I'm trying to show you is that it's better to use the definition for the sum of the xi's rather than doing direct calculation. So what am I trying to say? Well, I'm saying look at this sum. It doesn't look very easy. What I'm going to try and do is I'm going to try to change it into another binomial distribution. Why is that? Because if I change it into another binomial distribution, I know it sums to 1. So that's the trick I'm trying to do here. Okay, so for some of you who like math, you can listen. If you don't like math, you don't have to care. We're not going to see anything much harder than this for the rest of the course. Okay, so n factorial is n times n minus 1 factorial. I take it outside. P to the x is p to the x minus 1 times p, so I can take one of those p's outside. So I have now the sum, n is, well, I have this one, right? This I haven't done anything, so if I go from this line to this line, all I've done is I turned n factorial into n times n minus 1, I've taken it outside. I've turned p to the x and p to the x minus 1 times p. Okay, so that's what I've got now. So now how do I do this summation? Well, all you need to do in this summation is you're going to change the limits. I'm going from 1 to n, but if I go from 0 to n minus 1, I might be in business. So if I make the summation, change the summation, I set y is equal to x minus 1. So n minus 1 factorial remains the same. n minus x minus 1, I get there, and x minus 1 factorial, p to the y, 1 minus p to the n minus 1 minus y. Okay, so basically what I'm saying is if I make the substitution y is equal to x minus 1, this binomial, this ratio of factorials becomes n minus 1 choose y, you can check it, p to the y, 1 minus p to the n minus 1 minus y, times n times p. Okay, so what's the point? The point is that this expression here, this is a binomial, the probability mass function for a binomial distribution whose success probability is p and has n minus 1 trials. So the sum, y is 0 to n minus 1, this whole sum is equal to 1, and you get n times p. Okay, and that's basically one trick. That's a trick of computing directly the expectation of x. So you can see that okay, so I'm a mathematician, and you know, I've been doing this calculation for 20 years, but you're not mathematicians. You're more interested in doing things in computer science or engineering, so you don't really care about doing all these tricks. Or you might, some of you might be closet mathematicians. There's nothing wrong with that. And you get n times p using this calculation. And this is the trick you can use. And you can imagine that computing the expectation of x squared, so I put the square here, I had to put a square here, it's more difficult. In fact, it's not so trivial to do this calculation of x squared. It's really painful, actually. You wouldn't, in fact, you wouldn't do it. You would do something else. You would just use the definition that we talked about on the slides, i.e. we use, we would use this one here, and you would try and compute the expectation of x squared from this one. And in fact, there's an even better way of doing it. But what's the point I'm trying to make to you? Well, I'm just trying to say that the reason some of these theorems, this is a theorem, I wouldn't call it a theorem, but let's suppose it's a theorem. The reason one of these theorems are sometimes not proved is because sometimes the calculation are a little bit tricky. I personally I can do them all for you, but and we're going a bit fast, so I can potentially do this one for you tomorrow. Okay, we have much more, but maybe we'll just finish with this slide because it just summarizes things very nicely for tomorrow. Okay, so we'll just finish with one slide. We've got 6 minutes left, and we'll probably finish in 2. So the key points about this binomial distribution, I call it binomial distribution. You need n repeated identical and independent Bernoulli trials, and I make it clear that basically, so this basically what I say, IID, independent identically distributed Bernoulli trials of the set, which means that the success probability is the same. It summarizes all these 4 things. If you say IID Bernoulli trials, independent and identically distributed Bernoulli trials. So you need n repeated Bernoulli trials. Bernoulli trials means you've got 2 outcomes for each of those Bernoulli trials. The success probability is p, and the trials are independent. Okay. So a random variable x, which is the total number of successes in these n independent Bernoulli trials, and x is distributed binomial np. Okay, and so I'm happy to go through the experiment, but we're going very fast. I want to do 1 more 2 calculations tomorrow before we start these. So that's what we'll do. So we'll finish a little bit early today, and we're going to see much more on the binomial distribution and negative binomial distribution, I think, as well tomorrow. Yeah, and I have some nice slides for this as well to add on. Thank you for your attention. I'll see you tomorrow.